So here is the CCT diagram again, and we have spoken about different paths of cooling and the microstructure that would develop through such paths. And we have also seen, in order to form martensite, what could be the cooling path. Okay, so this is through this path 4 that you could produce martensite if you have a cooling rate that path 4 indicates here. So what we want to do today, we want to understand the transformation along this path, path number 4. Okay, so that is nothing but quenching, and as we have seen before, if you do quenching, then the steel is going to transform to a phase called martensite. Okay, and this particular transformation is quite different from all other transformations that we have talked about, particularly the pearlite transformation that we have discussed. It is very different from that in the sense that the change which occurs here in terms of the crystal structure change comes about by a very different mechanism. Okay. In case of the pearlite transformation, we know there is enough time for the diffusion to occur, and therefore the atoms can move and arrange themselves into a different pattern to come up with a new structure for the new phase. Okay. That is not going to happen in case of martensite, because you are not allowing that time for this diffusion and this rearrangement of the atoms by movement of the atoms. That time is not allowed. Okay, because here we are quenching it and the cooling rate is so fast that the phase is forming almost instantaneously. The moment you drop it in a bath of water, it is transforming to martensite, right? So because of this lack of time, the diffusion will not occur, and therefore for this parent phase austenite to change to a different structure, there has to be a different mechanism altogether, because here, as I said, the whole transformation is occurring diffusionless. Okay, so that is the first term that you should talk about whenever you refer to the martensite transformation. It is diffusionless. Okay, there is no diffusion occurring at those kind of temperatures below ms where this martensite will form. Okay. So in this quenching process, as I said, this is occurring without diffusion. So this transformation of austenite to martensite is also referred to as a diffusionless transformation. Okay, and therefore, as I said, we need to understand as to how the atoms would rearrange to give rise to a new crystal structure belonging to the martensite phase. Because we know whenever a new phase forms, the structure also changes, right? For example, if you see it for the pearlite transformation, austenite is transforming to ferrite and cementite, and both of these two phases in the pearlite have different crystal structures compared to austenite. Okay, austenite is FCC and ferrite is BCC. So here also, when you talk about a transformation which is giving rise to martensite, here also the structure changes, and the crystal structure of martensite is body centered tetragonal. Okay, BCT. So here it is changing from FCC of the austenite phase to BCT of the Martensite phase. Okay. But as I said, there is no diffusion here for the atoms to move and rearrange into the new structure. So therefore, we have to ask the question here as to how does the atoms then move and rearrange themselves to generate this new structure of Martensite. Okay, how does the structure change from austenite FCC to Martensite BCT? Okay, so that is what we are going to discuss in this lecture today. So in order to understand this, you will have to get familiar with a few terms, few terminologies and concepts such as these. So these are few terms that we are going to use to understand this transformation, particularly this change in the structure. So just make a note of it, and then we'll go about all this as to how these terms come across here and how they are relevant to this particular transformation. So what we are talking about here, as I said before also, a change in the crystal structure from FCC to BCT, but without the aid of diffusion. Okay. So therefore, we need to understand as to how do the atoms rearrange to generate a new structure. If it is with diffusion, then the bonds between the atoms will break, and then the atoms can move to a new structure. They can arrange, the atoms can move and get arranged into a new pattern to generate the crystal structure of the product phase, which is forming from the parent phase, right. So that kind of process where this bond breaking and diffusion occurs is known as the reconstructive transformation. Okay, and if you are doing the transformation at a temperature where diffusion cannot be conceivable, then in that case it has to be by a mechanism known as displacive, okay, which is also known by a Shear mechanism of phase transformation. Okay. So here what we are saying is with some small movements of the atoms, will rearrange themselves into a new pattern. instead of entirely breaking the bonds and then getting rearranged into the new structure. So here, instead of breaking the bonds, the new pattern of the product phase forms through some small movements, some coordinated movements of atoms across the interface between the parent phase and the transformed phase. Okay. What I mean by that, you can see it from this schematic. If I draw it here, let's say this is my parent lattice with a certain arrangement of the atoms like this. So I am using a dark circle to indicate the alloying element. In case of steel, it would be carbon. Okay, and the open circles would represent the atoms of the parent. Okay. Okay, so something like this, I am not going to draw all the atoms. So from here, you could understand the pattern in which the lattice is formed. Okay. For example, here if you see, there are 3 parent atoms and 1 solute atom, right? So that is the arrangement of atoms that you have in the parent phase, which could be the austenite in this case, if you are talking about austenite to ferrite or austenite to martensite. Okay. Now, this arrangement, that is this particular pattern that you have, this could change to a new pattern altogether by breaking these bonds, and that would happen in case of the reconstructive mechanism. And what would that give rise to? This pattern that you see over here, that is going to break, something like this. So here we are talking about a pattern like this, which is different from the parent metal. Okay. So if I draw an interface over here, across this interface, you would see how the structure would change. So along this interface, it is all the same. But below this interface, you are going to get the structure of the parent metal, like how it is here in the beginning. Right? I did not draw all the atoms here. I just want to show that there is some change that you can see over here in the pattern, right? Between this transformed phase and the parent, right? And this is the interface between these 2 phases, right? And for this, we have to break the bonds for the atoms to go from this arrangement to this new arrangement. Okay, that is why this is known as reconstructive. But if it is through a displacive kind of mechanism, then instead of breaking up the bonds, you could try and shift the atoms little bit. Okay, so with some small amount of movement across the interface, a new pattern can be generated. Okay, something like this. So now I cannot have a shape like this if I want to have a small movements of the atoms for the new pattern to form. Then this will be associated with some amount of shape change or shape deformation, something like this. Okay. So now across this interface, you could see that if we can move these atoms a bit like in this manner now, we would be able to generate a new pattern which is like this. But this does not require the bond breaking that we had in case of the reconstructive mechanism, right? Here only by some amount of movement of the atoms along the interface, you could see that a new pattern is getting generated. Okay, but as I said, when that happens, this would lead to some kind of shape deformation. And this is sometimes also referred to as shear mechanism, because this shape deformation that you have, this can lead to generation of shear in the lattice. Okay, and that is what we are going to talk about while talking about Martensite transformation also, because whenever we talk about Martensite transformation, this shear term would always come, the shear mechanism of this phase transformation, right? So the origin of the shear term is this, because here you could see some displacement of the atoms leading to some kind of shape deformation, right? So in case of Martensite transformation, we know there is no reconstruction because there is no diffusion, and therefore it has to be through this displacive or shear mechanism, okay, where the atoms would move to generate a pattern which is more relevant to the Martensite structure, okay, as it is cooled down below the MS temperature where the austenite phase is not stable. Okay. Now you could see something very interesting here as to what is the difference between this reconstructive and the displacive mechanism. Just to understand what is the role of this diffusion, or what is the implication if diffusion does not occur, or if it is occurring at a temperature where the diffusion is very limited, not conceivable. Okay. So then for that I would like to go to this particular diagram over here. Let's say this is my austenite parent phase, okay, this one having a particular structure, and also it's having a particular shape in the beginning. Now if I let it transform by a displacive mechanism, it would lead to a shape deformation, as I said, right? which is like this. Let's say this is transforming to the alpha phase, and if it is allowed to happen through the displacive mechanism, then it would lead to a macroscopic shape deformation also. Now, if diffusion is allowed and this segment that you see over here in terms of this triangle, if it is allowed to transport by diffusion to this side, then what is going to happen? Can you see that? Let us see. I will transport it to the other side, all the way to the other side. Okay, now it is transported. What do you see? The shape deformation that you had, that is completely eliminated. So it is again looking like the same shape of the parent phase, right? So that is the implication of diffusionless process, or if you say diffusion is allowed or not allowed. Okay, that's the implication that you can see from here. If diffusion is allowed, this shape deformation would be eliminated by the mass transport. If diffusion is not allowed, then this shape deformation is going to remain and give rise to some kind of strain in the parent lattice, because the parent lattice would restrict this shape change, right? What is the meaning of this? The meaning of this is, if the diffusion is not allowed, then I would have a shape deformation which cannot be eliminated, right? So that is what is going to happen in case of Martensite transformation. And by now, I hope you have some understanding as to what is the meaning of this displacive or shear. Okay, so Martensite transformation is going to be all about this, but there is more to know about it, because we have to see how exactly it happens and what are the other implications of this displacive mechanism. Okay, right. So we are back here, and now you can see that there is no force here. So you have to understand what is happening. See, if it is a mechanical deformation, the driving force is the mechanical force. If it is a plastic or elastic deformation, whatever it is. Okay, but here the driving force is the chemical energy, or the chemical free energy, or in other words, the Gibbs free energy. Okay, we are cooling down the austenite phase to a temperature where it is not stable, right? So it has a driving force to change to another structure. And if it is cooled under certain conditions where ferrite cannot form, then the only other phase which could form is martensite. Okay, so the driving force here is different. Although you see some amount of deformation like this, which is resembling the macroscopic deformation that you would obtain in case of a mechanical deformation or a plastic deformation, but the driving force is different. Okay, in one case, for the mechanical case, the mechanical deformation case, the mechanical force itself is the driving force, but here the free energy is the driving force. Okay, so when it is cooled below ms temperature, since it has to go to the martensite phase, the atoms have to move. And as I said, there are two ways the atoms can move. They can move by diffusion, by breaking the bonds, if it is allowed, if it is at a temperature where that can happen. If it is at a temperature where that cannot happen, then across the interface there will be slight movements to a new pattern, as you could see in this particular diagram. So that is why it is called displacive, as if the atoms are getting displaced with respect to their original position as it was in the parent phase. And with the help of this displacement, this coordinated movement, they are able to get arranged into a new pattern corresponding to the crystal structure of the product phase. Okay, that is why it is called displacive. Right, so once we have understood this, now we can go to the other terms that we have listed out over here. We still did not talk about the crystal structure change as to how does it happen from the FCC to the BCT? I mean, what is involved in that process? Displacive mechanism, that is a theory, that is fine. I mean, as a theory, that is good for us to understand how the atoms could rearrange to a new pattern. Okay. Ultimately, what happens due to this, that is something that you need to understand. Whether it remains like this or there are some more that you need to bring in over here to ultimately get the structure of the Martensite, which is practically obtained. This theory should be able to explain that. So far, we have not done that. We have only understood how the atoms would move when the temperature is brought down below ms. But how a unit cell of FCC is changing to a unit cell of BCT from cubic to tetragonal, that is something that you need to understand. Okay. So that is a process which will be given by this particular term over here, Bain distortion. Okay. So this is something that we need to understand into little more detail as to what is involved here and how does this kind of distortion would lead to a new crystal structure altogether. Okay. So I think we can take it separately in the next lecture and discuss more about it to fully understand it. Okay. So I hope today we can stop here.